Hello everyone, welcome back to my organic chemistry mini lecture. Today we will talk about the stability of alkenes and then the name of the alkenes with the cis-trans or ZE isomers. First, this is the ethene. That's the parent of all alkenes. Okay, so that's the first member of alkene, and there's a double bond between the two carbons, and both carbons are sp2 hybrid, and 4 hydrogens. And if you look at the orbital overlap of this ethene, each carbon will form 3 sigma bond, and the 1 sigma bond between these two carbon. Okay, and then also a pi bond. The pi bond is formed from the side-by-side overlap of the two p orbital from the two carbons, and the overlap is side-by-side here. I show that's a pi bond. Usually pi bond is weaker than sigma bond. Okay, and the pi bond will be broken if you rotate this single bond. So that's why double bond is rigid. Okay, now if one of the hydrogen replaced by other group, then that's called a monosubstituted alkene. And for example, this is the example that's a propene. One of the hydrogen replaced by methyl group from this ethene. We call these two carbons of the double bond vinylic carbon, and we call the neighbor carbon. Okay, the neighbor of the vinylic carbon is called allylic carbon. So in theory, if you have more substitution, you could have 4 allylic carbon in one of the double bond. Okay, and if you have more substitution, for example, the other hydrogen replaced by other R group, it could be different. R could be the same. Okay, I just use R1, shows it could be different, but actually it can be same. That's called a disubstituted alkene. And if the two substitution on the same carbon is called a geminal disubstituted alkene, and they can be on a different vinylic carbon. For example, this is called a cis disubstituted alkene, and because these two substitution on the same side of the double bond, same side. If they are opposite side like this, that's called a trans disubstituted alkene. And if you have one more hydrogen replaced by other R group, again, this could be different, could be same with the other substitution. That's called a tri-substituted alkene. And the last hydrogen can be replaced, and then that called a tetrasubstituted alkene. You may notice I have the potential energy here. Increase means the stability will decrease from here to here. Less and less stable. So tetrasubstituted alkene is most stable, and then trisubstituted, and then disubstituted. In disubstituted alkene, the trans disubstituted is more stable than cis disubstituted. Cis disubstituted is similar with the geminal disubstituted alkene. Okay, the stability is similar, and then monosubstituted is less stable. The least stable is this ethene, the parent. Okay, so what's the reason? Okay, there are two reasons. First is the electronic reason for this stability order. Okay, if you look at this, I use this example, the propene. If you have the substitution, then the pi star of the double bond, which is a anti-bonding molecular orbital of the double bond, can be stabilized by the neighbor sigma bond. For example, if you have an alkyl group, you have a carbon hydrogen sigma bond, electron can donate to this empty pi star. That donation is called a hyperconjugation. That can stabilize the double bond. So if you have a more substitution, they will have more hyperconjugation, and so the alkene will be more stable. So this is the electronic reason. Steric reason is if you have more substitution, and they will block the reaction between the double bond with the other reactant. So if you have a more substitution, the alkene will be less reactive. If it's less reactive, of course, it's more stable. That's why. Two reasons, electronic reason and the steric reason, more substitution make the alkene more stable. Okay. Now let's talk about the cis-trans isomers. So we still use this disubstituted alkene as example. This is the 2-chloropropene. There are 3 isomers, and for this first isomer, there's no cis-trans isomer. Why? Because one of the vanillic carbon has same attachment. I didn't draw that, 2 hydrogens. That's the same. And that's general. If you have any alkene, if one of the, or even both, okay, at least one of the vanillic carbon, if has same attachment, then there's no cis-trans isomer. Another example here. So if you have this alkene, one of vanillic carbon has the same attachment, same group, that's methyl group, same, then there's no cis-trans isomer. It doesn't matter what the other vanillic carbon. They could have the same or different, no matter what, as long as just one of the vanillic carbon has the same attachment, no cis-trans issue. Now, this is cis. We just talked about that because methyl and the chloro group are on the same side of the double bond. Okay, that's cis isomer. And if they are on the opposite side of the double bond, that's called a trans isomer. Other example, okay, this cis isomer can also called Z isomer. Okay, Z means same side of this 2 group. And a trans isomer is also called E isomer. Okay. Now let's talk about the other example. So this example, I have a nitro group and ethyl group on the same side of the double bond. So this is a cis isomer, or you can say Z isomer. Now, if they are on the opposite side of the double bond, then that's called a trans isomer or E isomer. So for disubstituted alkene, you can say cis-trans, okay? And cis means Z or trans means E. If you have a more substitution than 2, then you cannot say cis-trans. You have to can only say Z or E, okay? So I'll give you one more example of this disubstituted alkene. So this is a cyclic, okay, a cyclohexene. And you can see, look at this double bond. The substitution of the double bond is on the same side of double bond. So this is a cis isomer or Z isomer. In theory, you could have a trans isomer, however, because it was ring locked. So this can only be cis, cannot have trans isomer. Okay. Now let's talk about the tri-substituted alkene. Okay. Like I just said, if you have more than 2 substitutions, the alkene cannot call the cis-trans. You can only say Z or E isomer. For example, here. So now there are 2 steps to tell or assign the ZE. Okay. So first, you have to tell the priority of the 2 attachment of each vanillic carbon. Okay. So for example, this vanillic carbon have a 2 different group, chloro, bromo, and you have to use the CIP priority rule. Okay, we talk about this in my another mini lecture, and that mini lecture, and this CIP rule used to assign the R or S, the absolute configuration of asymmetric center. Same rule. Okay, so since bromo has a higher atomic number than chlorine, so this bromo is higher priority. Now look at the other vanillic carbon. Deuterium and hydrogen, they are same element. They are isotope, so you have to use a mass number. Okay, deuterium mass number is 2, hydrogen is 1, so this is a higher priority. Now, second step. Look at these 2 higher priority. If they are on the opposite side of the bond, that's called E isomer. Okay, if they are same side of double bond, that will be called Z isomer. Okay, but for this example, it's E isomer. Another example here, we have this vanillic carbon, we have methyl, ethyl. Ethyl is higher than methyl priority. The other vanillic carbon, we have a hydrogen, methyl. Methyl is higher than hydrogen. So now we have second step, compare these 2 vanillic higher priority group. They are on the same side of double bond, so this is Z isomer. So you can see E isomer is kind of like a trans, but you cannot say trans since this is tri-substituted. Z is more like a cis, but you cannot call it cis. You can only say Z. Okay. Now, last example here. We have the first vanillic carbon. We have a T-butyl and isopropyl. T-butyl is higher priority. The other vanillic carbon, we have hydrogen, fluorine. Fluorine is higher. Okay, that's because atomic number. So now this opposite side of double bond. So this is E isomer again. Okay, that's tri-substituted. What about tetra-substituted? I'll give you 3 examples of tetra-substituted. Okay, and for this one, again, use the same rule, right? Chloro, methyl, so chloro is higher, okay? Use this CIP rule. Chloro is higher than methyl. Bromo is higher than methyl. So 2 higher priority group on the same side of the double bond, so that's the second step, that's Z isomer. This example, we have isopropyl and ethyl on this vanillic carbon. Isopropyl is higher. And then the other vanillic carbon, methyl and nitro group. Nitro is higher because nitrogen has higher atomic number than carbon. Okay, so that will be E isomer. And then last example here, we have a triple bond here and a methyl group here. So this triple bond higher priority than methyl. And then ethyl compared with cyano group, cyano is higher than ethyl. This higher priority are opposite side of double bond, so this is E isomer. Okay, in some natural products such as the olive oil, they are double bond here. Okay, so olive oil is actually the esters of the glycerol. Glycerol is a triol, so this is a triglyceride. And this part is the long chain. We call this acid. Okay, if it's not ester, the acid is a fatty acid. Okay, and for this example, if this is acid, it's oleic acid. Anyway, this double bond, you can see the double bond is disubstituted alkene. And these 2 substitution on the same side of double bond, so this is actually cis, or you can say Z. You can say Z or cis, that's okay, because it's disubstituted alkene. And this is also Z, and this is also Z. Okay, so that's example. Okay, there are many other natural product with double bond. Okay, if you're interested, you can maybe Google it. Okay, search it for it. Now let's talk about how to name, okay, of those compounds with more double bond, like a diene or triene. Okay, this is example of diene. You have 2 double bond. First step, you need to name it. Okay, when you name it, don't worry about the Z or E. Okay, first just name it. So you follow the naming rule. Number it, number of carbon 1, 2. Why you number this carbon as 1? Because you will have the lowest number of the first substituents, chloro group. Okay, 2, 3, 4, 5. So this name is 1 chloro, 3 methyl, 1, 3 diene. Okay, penta, 1, 3 diene. Penta means the 5 carbons, the longest chain. Now worry about the ZE isomer. Okay, so worry about the first double bond, and we have a chloro and hydrogen, so chloro is higher. The other one is also hydrogen and this whole vinyl group, so that's whole group is higher priority. So for the first double bond, it's a Z isomer. Now look at the second double bond. We have methyl and chloro-vinyl group, that's higher priority, and also methyl hydrogen. Methyl is higher priority, so they are opposite side of the double bond, so that's E isomer. Okay, so that's why the final name, it's 1Z3E, 1 chloro, 3 methyl, penta, 1, 3 diene. You have to include this configuration of the double bond. Now, example of triene, we have 3 double bond here. So follow the procedure first, just give a name, okay? So, and you need to number it. Number, this is 1 because double bond will be lower number. You don't want the number, this is 1, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so, and longest chain is 9 carbons. Okay, so the prefix is non, okay? And then we will give the name of this compound without worry about the ZE issue. Okay, so that's a 3 bromo, 6-iodo and 5,7-dimethyl nona 2,4,6-triene. Okay, so now let's worry about the ZE, okay, isomer. So first, this double bond, we have a methyl and a hydrogen. Of course, methyl is higher priority. The other vinylic carbon, we have a bromo and a carbon. Bromo is higher, so this is a E isomer. And then worry about this double bond. And we have hydrogen and this whole group, that's a bromo-vinyl group, that's of course is higher priority. Now the other vinylic carbon, we have a methyl and this vinyl group, of course this is higher. So that's opposite side of the double bond, so this is another E. Now worry about the last double bond here, iodo, and this group iodo is higher because that's carbon, so iodo is higher. Now methyl and ethyl is higher, so this is Z. So final name will be 2E, 4E, 6Z, 3 bromo, 6 iodo, 5, 7 dimethyl nona, 2, 4, 6 triene. Okay. Okay, last minutes I will talk about some natural product with double bonds. Okay, for example, vitamin A. It's you need this every day. Okay, so you see a lot of double bonds here. Okay, so it's alcohol though. So let's look at the ZE configuration of these double bonds. For example, this one. Okay, so this one we have 2 on this vinylic carbon methyl, and this is methylene with more carbon. So this is a higher priority. This is higher priority than this. So I'm sorry, this double bond here is higher priority than this one. So this will be E. For this double bond, we have higher priority, opposite, that's also E. For this double bond, higher priority, that's also E. For this double bond is higher priority, opposite is also E. This double bond, higher priority, opposite, that's also E. So that's all E, okay. So this is the vitamin A. Another example is vitamin D3, and we have a 3 double bond here. The first double bond here actually has no ZE issue because this vinylic carbon has same attachment, 2 hydrogens. And this double bond, we have a higher, that's Z. This double bond, we have a higher and higher, that's E. So that's 2 different configuration. Okay, I think this example can help you understand the stability and ZE or cis-trans isomer of alkene. If you have any question when you study, please let me know. Okay, good luck.